In this video, we're going to expand upon our knowledge of esters and look at how the naming system works for compounds that contain an ester linkage. Now, the first thing to do when naming any organic compound, ester compounds included, is to identify what the parent chain of the molecule is going to be. Now, in ester compounds, this is actually relatively simple to do because all that we need to look for is the half of the molecule that used to be the carboxylic acid before the dehydration synthesis reaction occurred. So we can see in the top right molecule here that because the leftmost carbon here has an oxygen that links it to another carbon here, but more importantly because this carbon contains a double bonded O, we can see that this side used to be the acid side, or used to contain the acid functional group before the dehydration synthesis reaction occurred. From this, we can conclude that this is in fact the parent chain of our molecule, in which case we just need to count carbons, 1, 2, 3, 4, which means that the parent compound here is going to be butane because it has 4 carbons and because the only carbon-to-carbon bonds are single. Now, the only thing that needs to change is the suffix. We can't call this butanoic acid anymore because it's no longer an acid, it's an ester, and the parent chain of an ester functional group is given the suffix OH. So the parent chain of this ester-containing compound is what we call butan-OH, which I will now spell correctly, butan-OH, and there we go. Now, the only thing that remains is to identify the side chain that used to be the alcohol. Now, here we can see that this side chain contains 1, 2, 3 carbons, and so this is going to be a propyl, and actually that's the name right in a nutshell. So the side chain that used to come from the alcohol before the dehydration synthesis reaction is written on its own, separate from the rest of the molecule, and then the rest of the molecule's name is simply written here. So this relatively simple ester would be called propyl butanoate, and no locations are necessary because it's implied that this propyl is bonded to the oxygen in the ester, and we don't need to specify a location for OH because the ester always falls on carbon 1, as is the case with acids. Now, if we are to take a look at these two examples here, where the parent chain has a lot more complications, i.e. it actually has side chains, we would name it in more or less the same way. So if we identify the parent chain here, we can see that our parent chain is butane because, again, 1, 2, 3, 4 carbons, only single bonds. So the ester here would be called butanoate, and we can see that this is the parent chain because carbon 1 here contains the double bond O that used to be part of the acid functional group. We can see on carbons 2 and 3 that we have a dichloro, so therefore 2,3-dichlorobutanoate makes up the core of our ester compound, and we can simply write that in like so, and then the side chain that used to be the alcohol before the dehydration synthesis reaction occurred, we can see has 1, 2, 3, 4 carbons here, so this is what we would call butyl 2,3-dichlorobutanoate, and let's write the butyl a little bit more closely, and you can see that the butyl is actually separated by a space, no hyphens needed, to indicate that this is separate from the rest of the atoms that are now part of the acid side of our ester here. So this would be called butyl 2,3-dichlorobutanoate. Then if we take a look at this, there is no limitation on whether esters can form with ring structures, so we can see the beginning of our ester compound here. The side that used to contain the alcohol is going to be a cyclic compound because it is a ring structure here. There are 6 carbons, and this is not part of the parent chain, so cyclohexyl makes up the beginning of our name here. I'm just going to write that again down here when we write the complete name of our molecule. Then we can see our parent chain has 1, 2, 3, 4, 5 carbons, so here our ester compound is going to be pentanoate because it is 5 carbons, only carbon-to-carbon single bonds, and has an ester on carbon 1, which leaves our side chains to be 2,4-dibromo because we have 2 bromines on carbon 2 and 4, and then we've got a 3-ethyl, a 2-carbon side chain on carbon 3. So cyclohexyl is our side chain that came from the alcohol that is now part of the ester, and then after we would write everything else that is attached to the main parent chain here, starting with our 2,4-dibromo, followed by our 3-ethyl, and then the name of the parent chain proper, which is pentanoate. So in summary, if we use our most complicated example here, we name the side chain that came from the alcohol that underwent dehydration synthesis to make the ester completely separate as an alkyl branch at the front, and then we would name the rest of the side chains that are part of the main parent chain that used to contain the acid, so that would be 2,4-dibromo, 3-ethyl, and then name the parent chain proper, which would be pentanoate, 5 carbons, only single bonds, containing an ester that used to be the acid functional group. In the final video in this series, we're going to go over the naming system of amide molecules and the concern of having substances that are bonded to nitrogen and the complications that introduces as far as the naming system goes.